So we have fluid dynamics, question 29 I have discussed. Question 30 is there. The graph shows the viscosity of a butter. As you can see, the viscosity, a student want to spread butter on some bread. Explain why it is easier to use a butter at room temperature than straight from the refrigerator. So what could be the reason for that? When we are using a butter just straight out from the refrigerator, why it is not useful as compared to when we are spreading the butter at room temperature?
Because it's when it's out from the fridge, it's more solid,
Yeah.
and when it reaches room temperature, it
No,
starts to
see the
melt.
graph. Check the graph. What graph is shown here? The graph
Oh,
is
the answer
shown.
from the graph.
Yeah, you can see
Okay.
the viscosity. What happened to
Yeah.
the viscosity of a butter? Like when there's a smaller change in a viscosity for about 2 to 3 degree change in temperature. But when the temperature changes from that 5 to room temperature, there's a drastic change in a viscosity. The viscosity decreases. As the viscosity decrease, what will happen to the fluid? The fluid can flow easily, like the butter can flow easily, or it can easily spread on the bread. Is it clear?
Yeah.
So the viscosity is lower at high temperature or a room temperature. So as a result, the butter at high temperature will have less like we need less force is required to spread the butter, or less work done we have to do, so it can spread out easily. That's how you should write the answer. Clear?
Okay.
The next is figure shows the movement of the air bubble. As you can see, the air bubble. Complete a free body force diagram for a bubble rising through the liquid. So the bubble is going up. And it is rising, and they did not mention it is accelerating or decelerating, but it is going up. So what are the forces acting on the bubble? First, there will be a weight which is acting downward. Then what about the viscous drag or the drag force? What about the direction of the drag force? The drag force always opposes the motion. So if the weight is acting downward, what about the drag force? The drag force will also act downward, and upthrust will act upward. Is it clear?
Yeah.
The next is it is
Wait,
observed that
sir.
the yes,
The drag force is going at the in the same way as weight,
because the
isn't it?
drag force always oppose the motion. In the question, the bubble is rising. So the if the bubble is going up, if the bubble direction of motion is up, what should be the direction of a drag force? Drag force always oppose the motion.
Yeah.
Clear?
Okay.
That's why I drew downward. If the bubble was going down, then the drag force will be upward.
Okay.
The next we have it is observed that the larger bubble reached the top of a column less time. The larger bubbles, as you can see, if the bubble is larger, it's going up at the in a short time as compared to a smaller bubble. By considering the forces acting, explain this observation? So how we explain this observation? Because the force which is moving the bubble upward is the upthrust. Okay. And upthrust depends on what? It depends on the density of the fluid. It depends on the volume of a displaced fluid. Or when object is inside the fluid, it also is same as the volume of the object, because the object is completely submerged. So larger bubbles will have more volume. If a larger bubble will have a greater volume, it means it will also have a greater upthrust. As compared to a smaller bubble, for a smaller bubble, the upthrust is equals to density of a fluid, volume of object, and gravity. The volume is smaller, so the upthrust will be smaller. As a result, there will be like larger upthrust means there will be a greater resultant force upward, or it will have a greater acceleration. So upthrust is greater for a large bubble. That's the first thing we'll include. And as a result, there will be a greater resultant force, upward force act on the bubble. So it will accelerate and reach in a short time. Is it clear, this one?
Yeah.
When the size is larger, the drag force will also increase, but the resultant force, the increase in drag force is smaller as compared to increase in the upthrust. If you see, look, upthrust depends on what? Upthrust depends on density of a fluid, volume of object, and gravity. And volume of object is, it's a sphere, so it is equals to 4 by 3 pi r cube. So upthrust increases with the radius cube. And what about the drag force? The drag force, according to Stokes' law, it is equals to 6 pi eta rv. So it is, the drag force is proportional to radius square, but upthrust is proportional to radius cube. So if the radius is double, the upthrust will increase by 8. But if the radius is double, the drag force will only be twice. So the structure answer should be, when the size of the bubble increases, the upthrust will also increase as well as the drag force will increase. But increase in upthrust is more than increase in the drag. So there is more resultant or greater resultant upward force, which cause greater acceleration to this air bubble. Is it clear? The concept of the drag and the upthrust?
Yeah.
So you should relate these points, comparing them, how they are changing. The following photographs were taken 0.33 seconds interval. So the interval between them is 0.33 seconds. The photograph 1 is time 0 second, then photograph 2, 3. Sketch below the two label lines to show the displacement of a smaller bubble and a larger bubble with a time for 4 images. So we have these 4 images and we want to sketch the displacement of the small bubble and the large bubble. This B is a large bubble and A is a smaller bubble. So you can clearly see the larger bubble is almost catching up with the smaller bubble. Why? Because as we know, the larger bubble will have a greater upthrust, or it will also have a greater drag, but it will also have a greater upthrust. So if I consider this as origin, because we have to consider the points as one of them as origin. If I consider B as the origin, the bubble B as the origin. So bubble B will have, bubble A is at the origin, not at the origin. It has a displacement, some distance displacement above the origin, and it is going up. Like it is accelerating constant because the upthrust drag. If we assume that I sketch on the axis for a displacement of these bubbles, so the velocity, it means it has a constant velocity. Like the displacement time graph, what slope represent? The slope represent the velocity. Okay. So as you can see, almost for B, for A, it is having a same velocity, like same displacement, almost same displacement every second. This is a displacement here, and displacement here. So it has the same displacement every second, or we can also say a constant velocity. To represent a constant velocity, how we represent a constant velocity? We represent by a straight line. And why I drew above the origin? Because if I consider B is at the origin, so A is above the origin. So this is a graph for A. What about B? When you see the distance covered by B, it also looks same. So B is also moving at a constant velocity because it looks like same distance it covered in a 0.3 second. But it is catching up A. So if it is catching up A, it means B is having a higher velocity than A. So to represent a higher velocity in a displacement time graph, we represent by a slope. A steeper gradient should be there. So if this is representing a B, so this will be the graph for B. It shows that the B is having a higher velocity than A for the same time interval. Is it clear? The two, because it's just a
Yes.
sketch, I don't have to number that. I just have to sketch the result. Is it clear?
Yes, sir.
Then the photographs are at a scale of 1 to 12. What does it mean? Like 1 centimeter is equals to actually 12. By using a measurement from a photograph, calculate the speed of a bubble between 2 and 3. So if I want to calculate the distance, calculate the speed. Speed is distance over time. Okay. So I will measure using a figure, I will measure the distance and then I'll multiply by 12. So using the scale, and it should be same identical point. Like if I'm using a surface here, I'll use this surface and this distance I'll measure by using a ruler scale. Let's say this distance is 0.5 centimeter. So 0.5 centimeter, the scale is 1:12. So what I will do, I'll multiply by 12. Like if it is 0.5, 0.5 will be multiplied by 12. Is it clear? So I'll get 6. And the 6 is the total distance in centimeter divided by time. The time interval between the photographs is 0.33. So I will get the answer in centimeter per second, or I can convert into meter per second. Is it clear, this one?
Yes.
So even in the question, especially in Edexcel, you use a measurement from the figures as well. Describe an additional measurement. A student wish to determine the drag force on the bubble. Explain why it might not be possible to use a Stokes law to calculate a drag force on the bubble. So if you are applying a Stokes law is only applicable for small sphere. But as you can see here, the spheres are additionally large sphere, and they are not perfect sphere. The spheres, like example, the bubbles are changing the size. So the size of the bubble, you can say the size of the bubble is large, or the fluid flow is not laminar around the bubble, or bubble is not perfectly sphere. That's why we cannot apply the Stokes law, because Stokes law is only applicable when when the object is spherical and the fluid flow around the object is a laminar. Then describe an additional measurement that you would take from a photograph and how it could be used to determine a drag. So assume that the bubble reaches a terminal velocity. So if the bubble reaches a terminal velocity, because for this bubble, there's an upthrust, there's a weight and a viscous drag. So viscous drag plus weight will be equals to upthrust. So viscous drag, the viscous drag will be weight minus upthrust minus the weight. So when we subtract them, so what we simply do, we'll find the weight, how to find the weight, mass into gravity, and how to find the upthrust, density of the fluid, volume of the fluid, which is same as the object. By using a formula 4 by 3 pi r cube, we'll get the volume. So we'll get the upthrust, we'll get the weight. When we subtract weight, upthrust minus the weight, we'll know the drag force. That's how it can be done. So using a formula will determine the volume of sphere, and using the mass into gravity will determine the weight of the bubble, and then subtract them to get the viscous drag or the drag force. So this is question from the fluid.